First, I'm just going to go over a brief summary of how I got to this point. So this is a engine management system for a BMW Mini R53. And the first video I did, I took this apart. And I got the circuit board inside. And in that first video, I tried to identify what all of these chips are and look up the data sheets for them and sort of work out the basic circuit on this system. And what I've done is I've taken 3 of the chips off. So the next video was taking the chips which I'd removed from the board. And this is a microcontroller with integral memory. This one is memory for this microcontroller, and this is the RAM for that microcontroller. But I concentrated on this microcontroller because these little pads here, I believe that this is some kind of JTAG interface, and this microcontroller is used to read and write to the memory of this microcontroller, which is the main ECU memory. So I believe that this microcontroller in the factory, they use this to program the ECU. So I want to get to the program of this microcontroller so I can work out how to use these pads, I believe, to program and read that memory over there. So for this video, I've got a file which I'm bringing in from the last video, which is the memory read from that microcontroller. And it says 32K because I've just read in all the possible address combinations that the actual microcontroller can have. But they're not all valid. There's only about 4K worth of program in there. But in the actual file, it's all binary. So in this file here, this is another file generated in the last video. If I display what's in that file. So this is actually what it contains in kind of a readable form. So these are all hex numbers. And at the bottom here, these are just like the interrupt vectors. If I scroll up a bit, there's an area of blank memory. And then above that, you can see that there's the actual program data. It only spans about 4K. So this is the start of the program memory area, F000, and start to get data there. So that was what came out of the last video. And I've got to somehow take that and make it into a form which I can understand. So I need to do what's called disassembling it. So it's all in machine code, but I can convert it into things called mnemonics, which are like just like human readable forms of that code. And the actual mnemonics you can find in the datasheet for the processors, but I couldn't find the datasheet I've got for this particular microcontroller. It didn't list the instruction set, but I managed to find on Wikipedia. It mentioned that it's based on 6502, so I got the instructions for 6502. But when I looked at them, although some of the instructions are actually the same, in fact, the 6502 instructions are pretty much identical, but there's a lot more instructions which are used on this microcontroller. So I got another 6502 instruction set, and that was nothing to do with it. So these are just in here as things which were like diversions from the thing. But I found there's a datasheet called for family 740, which is like the family of devices of this microcontroller, and I found the instruction set in that, and so that's what I used. So to start off with looking at what I've done for this video. So I've made myself a Python program here, which is to disassemble the M37477 microcontroller code. And in this shell script, I just call that, and I tell it what address I want to start to load the dump file at, which is 8000 hex. And then the dump file the binary data gets loaded into that area of memory that I'm analyzing. And I've also got a config file here, so I can add labels and things to the config file to help me work out what's happening in the actual program. And at the minute, I'm just sending it out to this ASM file, which I've generated one here, but I'll run the program again. But just before I do that, this is the config file. So if I look in here, so this allows me to say at a certain memory address, don't disassemble that memory. So what the actual disassembler will do is it'll start off with all the entry points it knows for the program for the microcontroller, and it'll start disassembling from each of those entry points. And then when it call subroutines or jump to subroutines, it will then automatically disassemble those areas as well. But there's an area which I want to block at the minute, so I don't know why, but there's a single area which I'm not quite sure what's going on. And then there's other things which I can put in which are forced to force areas of disassembly. So after I did the first set of disassembling, there were areas which will actually look like programs, which I'm pretty sure turned out to be valid programs because they look like it. But it didn't automatically disassemble those. Now, what it can do is it can do a thing called indexed addressing when it calls functions. So what it can use is an offset into a programmatical offset into a table of like call addresses. But if it does that, then you don't, because the program's not actually running, so you don't know what those values are. And so I've actually predicted what they are here. So that's helped me with the disassembly to this point. I've got a couple of example labels in here just to test my labeling facility. So when I actually come to working out how the program works, I'm going to have to be putting in labels and comments as I go, and then sort of slowly working out exactly how the program works. And then there's also system labels. So these are registers in the microcontroller, and they've got addresses. And what I can do is if I list them here, I can get it to automatically put these references into the actual disassembly. So it makes more sense rather than seeing an address C2, which I'd need to remember what it is. I can replace it with this port P1 so that I know that whenever it uses this address, it'll actually write in the disassembly port P1, which makes it a lot easier to read. I don't have to keep looking up what the addresses are. But that you'll see that when I list the assembly in just a second. So yeah, I'll just run this again. So you see I last ran it on 8.11. But if I run it again, you'll see that update. So when I run it, because it redirects the output to the assembly file, it just like gives you a brief description of what it's doing, and it runs fairly quickly to do what it's doing. Consider it's a Python script. And then it outputs this file. Actually, I'll just show that it's updated. So there it is. So it's now run at 3:43. So if I type more, so this is the output of the disassembly. So at the top, it just tells me, okay, I've loaded this dump file into that address, and it knows what the memory. So I'll go through the source code after this to like describe exactly how the source code has been written, and it's not a very big program. It's quite simple to do this kind of thing. But first of all, it goes through the memory in order, and it's found out that the top is RAM, and so in the disassembly, for certain instructions, I can work out or I can predict that those instructions have read or written or done certain things to the RAM, these RAM addresses. So on this 0 address, it's been read. I know that it's been written to. It's been had bits set and bits cleared, and it's also been used as an offset to a branch instruction. And then the next one's been used to read and to write, and the same again. And so just as I go through the assembly, I flag these addresses as if I know that that something's happened to them. That's not going to be completely accurate, but it will give me a good idea of what's going on in here. Also, I've just had a quick look at the entry point code, and I found out the stack pointer is set to this address 6E, so I've put in a label there. So this is the kind of thing I'm going to be doing as I work through the code, generating labels and comments, which I put in here to help me just work out how things work. And then it goes through another piece of RAM at the top, and I've also I can tell if the address has been incremented and decremented as well. So after the RAM, it comes across the register area. So this is where I've got all those labels, and I can, again, in the register area, I can tell when it's been read and written to for certain instructions. So I flag that, so that gives me an idea of what registers are being used and which and what's happening to them. On this one, that's not being used because it's interpreted it as a data byte. So if no operations happened on it, then it just like tells me what the value is. But that's arbitrary. It doesn't really make any difference. So it goes through all of the registers in the CPU and tells me basically the data that's happened to them. Then I get to another area of RAM, and as far as I can tell at this stage, that area of RAM isn't being used at all. And then I get to a void area. So in the microcontroller, there's an area of addressing which has no RAM or ROM, and so that's the void area. And I can flag if it looks like that's been read or written to, then that will tell me that I'm going in the wrong direction. But at the minute, there's nothing which says that anything's tried to read or write to that void area, so it's looking positive. And then I come to the actual ROM area, so it starts at F000. Now at the start of the ROM, it looks like there's some data bytes, and it says that these have been flagged as being read. And these other data bytes, they've probably been read as well, because they've probably been indexed off of this address and then read as an indexed sort of piece of data. But they also look like data. You can see that they're kind of ASCII characters. And then it gets into the start. Well, this isn't the start of the program. This is like some subroutines at the top of the memory area. And so it's doing the disassembly stuff. And in these square brackets is where I can put labels to tell me what these things are. So when it does a branch, so it does branch and it jumps 75 address spaces onwards. And I could, if I put a label at that address, then it would show me everywhere where it jumps to that address that it's going to that label. So I don't have to, so it makes it obvious when certain bits of code are getting called with labels. And also because it's using the 0 page, so address 10 in RAM, if once I put a label on that address 10, once I've worked out what that address is, then it will automatically put that label in these square brackets. And so I'll be able to read the code a lot easier. So as things progress, it will become easier and easier to read the code. I should eventually have a full idea of what it does. So if I just skip through a lot of this. So here's the actual entry point. So when I've got vectors at certain addresses, I put in here, so this is a vector for doing these CNTR 0 and CNTR 1, I'm not sure what they are, interrupt, which is a wake up interrupt, or a break interrupt, timer 4 interrupt, they all come to this area of the code, reset, so this is basically the start of the program, and timer 1 interrupt, so this is, and it looks, and this also validates that it looks like it's disassembling okay, because set interrupt disable status. So basically it's disabling the interrupt at the first, and that actually is what you would do in a microcontroller usually is make sure that you have a clean sort of thing to work with. So you've got clear decimal mode as well. So this is all looking correct. Clear transfer flag. And then here you can see this is where it's automatically putting the register number name. So it knows that address FB, which is that one, is the CPU mode. So it's loading hash means immediate number into 0 page, so it's loading 0 into CPU mode. So that's how it becomes a lot easier to read as I progress through the programming. But basically it's all a load of, at the minute, about 4K's worth of disassembled code, and so so this is a good stage to be at. So I'm at a stage where I'm going to start to analyze it now. But I've successfully managed to disassemble it. So here's the timer 3 interrupt, and again a validation because it says return from interrupt there. I've got return from interrupt instruction. So this is all looking like it's disassembling fine, and this is all valid code. And the next stage really is to analyze this and work out what it's doing, and then I should hopefully be at a stage where I can read right to the main memory on this particular ECU. But I'll just skip down to the end, and so because this is where the interrupt vectors are defined in the actual memory, so you can see that at the very end. And if I scroll up just a bit above that, so at the end it looks like there's a bunch of data as well, which it reads through lookup table. But I'll go over a brief description of the source code now and go over how it works. It's not very complicated. It's quite a small piece of programming. So if I open this up in a text editor and Python, so it's only, I haven't put it in classes or anything like that. It's just like a simple, I wanted to get this stuff done, and so I just put it into a single program. I'll just scroll up to the top of this code, and I'll also turn line wrapping off to make it easier to, if I can do that, text wrapping off so comments don't wrap around. So I just got the standard comments at the top. I don't have to include much. It's not using much in the way of packages or anything, like classes or anything. Then I've got some basic defines at the top, like you'd find at the top of any program, telling me how big the actual full memory map size is. These are the command line arguments, just the default values. And I define for the config file, so there's 3 things I put in the config file: block addresses, forced to disassemble addresses, and labels. And I'll probably add to that comments for when I actually do the analyzing of the actual code, because I'm going to need to put comments in there, otherwise it's going to be a bit tough to keep track of what I'm doing. And then so I've defined, you'll see just below here, the memory map, and then I define a map where I'm disassembling into it, and I sort of go through the memory map and I place the disassembled stuff into the disassembly map. But I'll describe that, and these are the various pieces of data which I can define for the memory maps and stuff, like end addresses and start addresses. And then there's memory types, so there's vectors, registers, or just standard memory. So that I have those definitions because I differentiate between them. There's the permissions that you can have on the different memory types. So void memory is memory which doesn't exist. Then there's type you can read only, which is the program memory, and read write for the RAM. And then this is where I flag. So I've got constants for the things that I flag, like when I flagged it in the data areas that the particular memory cells were written to, read from, incremented, decremented. I've just got like a definition of all the different types of things I can flag. So this is the config file. So I'll read the config file into like a couple of arrays to make it easy to use the block disassemble and force disassemble addresses. And then this is the memory map which I disassemble into. So for I create it for the full memory map size for each of these things, so I can have descriptions, labels, and memory itself. And I'll probably, when I do the comments, I'll probably add them to the descriptions, but I'll think about that. And then I have the memory map. So the disassembly memory map is where the target where I'm going to take data and place it into. But the memory map itself is where I read the binary file into, and then I iterate through all the memory here and place the disassembled stuff into the disassembled memory map. So it literally just goes through and says from address ranges what the type of memory is. If I scroll across, and I say what the permission is on the memory, if I want to do any kind of validation kind of thing, and I just have a description, so I can, at any point, I can actually bring up the description. So you've got the standard RAM at the top, then you got the microcontroller registers underneath that, so for each address I've got the different ports. This is all coming out of the datasheet that goes with the microcontroller. And then at the end of the memory, you've got the vectors, which are the entry points basically. So these are starting points at which I start to disassemble the stuff, and then it goes through subroutines and stuff, and I just automatically go down those branches when I come across them. And then this is from the datasheet as well. So most of this program is actually data, because from the datasheet I've got all the mnemonics for the machine operations. So the break instruction, array with, so this is what gets actually disassembled into. So the numbers get disassembled into these instructions, and these are the opcodes. So in the source file, in the source binary file, where you've got a value of 02, it then gets interpreted into this jump instruction. And what's also important is the number of bytes of the instruction. So this is 1 byte for the opcode, and then following you'll have the number of bytes which go with that opcode. In this case, one extra byte for the 0 page number. but you can have like 3 and possibly even 4. I think this one only this microcontroller only has up to 3 bytes. It might have some 4-byte instructions, but I think it's mainly 3 bytes. But in these, I've also like flagged things which I can do as well. So I can decide if it's a relative call, I use this information to actually go off and start disassembling down this branch, and then it can continue disassembling after this branch as well. It's kind of recursive programming. I'll go over that when I get to actual programming stuff itself, and I get descriptions for the machine language as well, which I just put in comments. They're not really that helpful unless you're not familiar with the actual microcontroller, and I'm not that familiar with the microcontroller, so they're slightly helpful to just have something which tells me exactly what the mnemonic means at the end of each line. But that you basically go through pretty much 255 instructions. There's a few which are invalid, so I've put this invalid text in so that if something gets interpreted as an instruction which isn't an instruction like this, it will show up clearly, and I can then say, okay, well, that's suspect. It doesn't look right if it tries to use an instruction which doesn't exist. So 255 stuff. There's still all going through data. So that all up to this point, it's all been data, no program. So if I was going to scroll to the bottom now and show how much program there is. So this is the program, and that's the program. So there's less program than there is data, and most of it's pretty basic stuff. So I'll skip over sort of most of giving a brief description. This is reading the dump file into memory. So the binary file which I got from the last video, this just reads it so that I can then use it in memory. Read config file, so that just reads the configuration stuff into arrays. Find memory. So because my memory map is separated out into RAM, registers, vectors, and ROM, what I do is I go through the memory sort of as sequentially. So if I'm at a particular address F0000, I'll go through to F0001, 2, 3, 4. But I need to know when I'm moving between the different memory types. So I use this to find which memory map, part of the memory map I'm supposed to be using for every particular address. And set memory, it makes it simpler because I can just give it an address and data. It will find the part of the memory map where I'm supposed to put that data in, and it will place that data in. So this just makes the function a lot easier. So this calls the find memory to find what part of the memory map it is for that address, and then it will set the data into that part of the memory map. And the same with get memory. So you just give it an address, it works out where in the memory map it is, it gets the data, and it returns the data. If it comes across a void part of memory, then it will return I think it returns a false if it does that. And then this is the main function, and this is actually called recursively. So recursive programming is fantastic because you do a task, and then within that task, if you want to do the same task, then you call that task again from within itself, sort of thing. It goes off down rabbit holes basically, and then it sorts itself out and comes back out, and everything's done quite neatly. So for each of the addresses that I start, so this, when I come in, this is an entry point. So this would be like a vector, or one of the places I put in the config file to like force disassembly at this address, or it gets called from within this function. So when it comes across a jump or branch instruction or call instruction, it will call itself and go off down that rabbit hole, and then within that rabbit hole maybe it will find another branch instruction, it call itself again, and it goes off down and down and down, and then when it's finished doing that instruction, it comes out, and then it finishes doing what it was doing before, then comes out again. Recursive programming takes a while to get your head around, but actually it's really, really very neat. But in this disassembly, all I'm doing is, if it's void memory, it'll give me a warning. I haven't come across any of those. Otherwise, it will it just gives me a note that I'm disassembling certain addresses. That's what comes up on the screen. It goes around the loop, and this is so this is where it increments the addresses and stuff. So for certain things, it comes out. So this is where I can set the block disassemble. So so for this particular address, which will be every single address it comes across, it says, should I not disassemble this? And if not, then it comes out of this particular iteration. And there's other reasons why you might want to stop disassembly. If it's already been, so yeah, there can be a subroutine within a program could get called from multiple places. But if it's already been disassembled, then it will just go, it will potentially go into an infinite loop if you just keep disassembling the same stuff. So it decides, has this already been disassembled? And if it has, then it doesn't have to bother disassembling it, because it will have gone down all of the possible paths after that. So that's another reason to stop disassembly. Then it says, okay, here's an address that I want to disassemble. So it gets the data for that address. It looks up the actual instruction which it wants to disassemble, and formats it into the output. So here I look up the mnemonic which I want to place in the disassembly. So this line is actually producing a line of the output disassembly there in this format. And then do some clever stuff after that, basically. So as I said, each instruction may have maybe between 1 and maybe 3 or 4 bytes long. So a single byte instruction would just be a mnemonic. Otherwise, I need to make sure I go through and get the data bytes associated with that instruction, which is stored in the definition of the instruction. So that makes it nice and easy. And I just display on each line of the disassembly after that the actual bytes. And then I decide, does the mnemonic which I had, does it, which is up here somewhere. It's back up here, back up there. Did that affect memory in any way? Like, did it read memory or write to memory? And this is all done through, like, in assembly language, the addressing types like indirect addressing, direct addressing, relative addressing. But from the operation of the actual machine code, I can decide if it's a specific address, which I can then identify, then I can flag that address as having been read or written or incremented, decremented, branched on, or had a bit set or a bit cleared within it. So I do that in this block of code for the different types of addressing mode. Here is where I increment the address to the next instruction. But then I decide if the previous instruction, because that wishes, so I'm on the next instruction there, but if the previous instruction, which is a stuff this side of the increment, was a branch instruction, then I decide how far it has to, so this is a relative branch, so it could be plus or minus 128 jumps. I decide how far it has to go, and then I set the address to whatever the address is plus that offset, so it will then start disassembling the other side of that branch. Or if it's an absolute addressing, ABS, where it gives you like the full address of where it needs to go now, it will set the address to the new address and start doing that. But if it's a call, it does two things. It sets the address to it works out what the new address is, but then this is the recursive bit, so it starts the function to disassemble the new address. But once it's finished doing that, it will come back to this code and it will continue disassembling the bit that it was at. So it's a bit complicated to think about, but it's just it's fairly simple when you know the concept. But that's basically pretty much it. So this is the main application. So I come in, I handle command line arguments. I do what I usually do if it doesn't look like there's enough command line arguments. I just display, okay, you should have these command line arguments. I just print out a message saying I'm dumping this dump file at this address. So when I get the file, at least then at the top of the file I can identify what it's disassembly of. read the config file, read the dump file. Those functions were at the top of the listings. And then I go through each start address. So every vector, so if the memory type is vector, if it goes through the memory map and it finds a vector, then it starts a disassembly there. So there it's doing the disassembly, and it's just telling me, puts a little note in saying that this is where this is starting because of this interrupt vector. And then also in the config file, I have the force disassemble, so it starts going down those disassembly points as well. And then after that, this location. Oh yeah, so after it's done all the disassembly, any stuff which hasn't been disassembled, it figures must be data. So it displays it as data basically. It just formats a string, displays the data in several formats so that it makes it easier to work out what's going on. And at the very end, this bit down at the very bottom, this is, so all it's been doing before this is taking the data from the source memory map and put it into the disassembled memory map. And now it goes through here and it just takes a disassembled memory map and it writes it out to the output file as it's required to be written out. So it just like goes through and just flushes everything out into the output file. And that's the actual program. It sounds probably more complicated than it is. There's a few advanced topics in there for programming, but at least now I'm at the stage where I've got a disassembly. Now the next stage is to not use a computer, and well, actually I will be using a computer, but it's not doing programming and stuff. It's actually going through the listing, working out what's happening, putting comments in and stuff, and then I can work out how to functionally use it. And hopefully in the next video I should explain how the functionality works, hopefully, and maybe even demonstrate, hopefully with any luck, doing some actual operations on the ECU, but I'm not sure about that. It's a bit too soon to know if I'm going to be able to do that.